Section 3.3 for college algebra is about properties of functions. And we've talked about even and odd functions in a previous chapter. It was chapter 2. I want to say it was maybe section 2.2, but I can't remember for sure. So you have a whole page of, maybe even 2 pages of notes for testing if a function is even or odd, which would be the same as saying if it has y-axis symmetry or origin symmetry. So you can refer back to those, but I'm also going to show you an alternate method to test that you might prefer. So remember that even functions are the ones with y-axis symmetry. So here's our y-axis. So they're going to look the same on both sides of the y-axis. Like I could fold it across the y-axis and it would exactly land on itself. The test point that we want to use is going to be the one that, like if I put a point over here, x, y, then the point that matches it on the other side that would reflect across would be negative x, y. So the test point was negative x, y. And what we had done in the previous chapter was replace the x with negative x and leave the y the way it was. And if it came out to be the same as the original function, then it would be an even function or have y-axis symmetry. Odd functions are the ones that have origin symmetry. And they are ones that if you flip the graph over, like rotate it 180 degrees around the origin, the graphs would look the same. So if I rotate this, if I hold the origin still and rotate the whole graph 180 degrees, it should look like I never moved it. The test point for odd functions if I put a point, like say up here, x, y, then the point that matches it would be this one down here, which is negative x, negative y. So the alternate, oh, that was a weird way to say that. The alternate method to test for even and odd is that we're going to sub in negative x regardless of what test it is. If the result is equal to f of x, so the same as the original function, then it's going to be an even function. If the result is equal to everything being the opposite of the original function, then it is odd. So I'll show you that test here. So we're just going to go ahead and test f of negative x in both of them. So we do f of negative x. When you do this test, really, really, really remember to substitute in with parentheses. So I'm replacing the x with negative x. So I want to replace that x with a parenthesis, negative x squared minus 6. If you don't get the parentheses in there, when you square it, you're going to have the wrong sign and it's not going to work out. The test won't be accurate. So then I'm doing negative x times negative x, which gives me positive x squared minus 6. And I can see that that is the same thing as f of x. So when I compare it, they are the same. So that makes this function even. Now I'm going to test on this one over here, f of negative x. And again, remember that you're replacing x with negative x. So get that in a parenthesis, please. So negative x cubed minus 5 negative x. And then when we do negative x times negative x is positive x squared times negative x again would be negative x cubed. And then negative 5 times negative x will be plus 5x. And what we're checking here is to see that all of these signs are opposite. All of them. They all have to be opposite. If even one of them is not opposite, it does not work. All the signs are opposite, which tells us this is an odd function. Okay, increasing and decreasing. So increasing and decreasing is referring to, like, if the function was a roller coaster, where it's increasing means that the function is going uphill from left to right. So increasing means the function goes uphill as we go left to right. So you're going up the hill in the roller coaster. Decreasing is where the function goes downhill from left to right. So we always want to imagine getting on our roller coaster at the far left end, so out there at negative infinity. And then we're going to talk about whether we're going uphill or going downhill, and then we're going to list our intervals where that happens. So when I get on the roller coaster at the left end, I can see that as I'm walking along it, I am going uphill, still uphill, still uphill, still uphill. And then here is where I get to the top and start going downhill, 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 downhill. Then the bottom of the section here, turn around, and I'm going uphill again. So on the function, I start out going uphill. And then once I get to this spot right here, this is like a turnaround spot. We're going to talk about those. And then I start going downhill on my roller coaster. We get to the bottom, we bottom out. That's another special spot on there. And then we start going uphill again. So looking at a function, it's pretty easy to determine where, like visually, the function is going uphill and downhill or increasing and decreasing. But what we need to do is use intervals of our x values to describe where that's happening. So imagine that you're an observer walking along the ground here, or this could be like a time interval, and you're going to say when or where, using x values, that function is increasing or decreasing. So we want to imagine that our time interval goes from negative infinity to infinity. So I'm going to say, okay, from negative infinity up until what time on this timeline does my function go uphill? So I can see it's going uphill all the way from negative infinity until right here where it starts to go downhill. And then it goes downhill along this time interval until I get to right here, and then it starts going uphill again. So we'll use these intervals to describe where the function is increasing and decreasing. And then, of course, we have these two special spots here where the function is doing its turning around. So when it's doing the turning around, we're not going to count that in the increasing or decreasing intervals. So we want to say that this function is increasing or going uphill. I'm going to use interval notation and then set builder notation. So interval notation, remember you get two numbers in each interval. Since I have two sections that are increasing, I'm going to have two intervals. So it's increasing from negative infinity until this number right here, which was negative 3. At negative 3, it's doing its turning around, so I don't include that. So I use a parenthesis. And then it starts increasing again at this number, which is 2, and it keeps increasing. After that, it doesn't turn back around. So 2 to infinity. In set builder notation, that would look like all the values of x such that x is less than negative 3, and or, so we use a comma, or x is greater than 2, not and. And then likewise for decreasing. Decreasing is where our function is going downhill, and that is in between the values of -3 and 2. At -3 and 2, it's turning around, so we're not going to include those. And set builder notation would be all the values of x, the set of all numbers x, such that x is trapped between -3 and 2. Now these top of the hill, bottom of the hill are, or I guess bottom of the valley, whatever you want to, however you want to describe that. Those are called local maxes and local mins. So a local max is like the top of a hill, and local mins are at like the bottom of a dip or a valley. Local maxes and local mins could be ordered pairs, but they can also be values. So if you're asked for a local max and local min value, remember that values specifically refer to y values when we talk about the value of a function. So the actual value of a max and min is its y value. So at these points where the graph turns, so goes from increasing to decreasing or decreasing to increasing, we would say the local max value is its y value. So here is a local max because it's up at the top. Its value is 3, and it occurs at x equals -3. Then we have a local min, that's down here. And we would say there's a local min at x equals 2, or we could say there's a local min at 2, -2. So there's a couple of different ways that you can talk about local maxes and mins. Just make sure that you are reading, the blue words on my math lab where it tells you how to give your answer, or the instructions when you're taking a test, so you know if it's wanting an ordered pair or wanting you to say it kind of as a more sentencey type thing. Absolute max and absolute min values are going to be like on a closed interval. So on a closed interval, you're going to have both an absolute max and an absolute min. If you have an open interval, you might have one or the other. You're just going to have to look and see. So it's like the absolute highest a graph can go. So this graph doesn't have either because it keeps heading down, 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 down. So forever. And this end keeps heading up, 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 up. So it's not going to have an absolute max or min that's a real value because it continues on towards infinity. But if I look on a closed interval, so on 0 to 7, so that's on this graph from 0 with a closed. So I'm just looking between 0 and 7, 3, 4, 5, 6. Well, 0 to 7 would be out here. Oh, no, I wanted that to be a 4. Hang on, let's change that to a 4 because 7 is off the chart. So change your 7 to a 4. From 0 to 4, which is here, from here to here, I would have an absolute max and an absolute min. So I'm just looking at the graph in between this point right here and this point right here. So the absolute lowest this graph goes is right here at 2, -2. So that is going to be the minimum, the absolute minimum value. It got cut off. The absolute minimum value is -2 because that's the lowest y value just on this interval. It's the only part I'm looking at is this part of the graph between those two ordered pairs. And then the absolute maximum would be over here at this ordered pair, which we're just going to kind of tell it a number, like 3/2 looks right, or 1.5. We'll just make that up. If you had an actual equation for your graph, you'd be able to plug in that number and figure it out. But my graph doesn't do that. So There's estimating. Okay. Let's practice also using our graphing calculator to find maxes and mins and tell where a function is increasing and decreasing. So we need to grab our graphing calculators. The first thing we're going to do is graph that function in y equals. So I'm going to go to y equals. Make sure none of your plots are turned on. If you have any plots turned on, it tends to mess up your graphs. So I have nothing stored in there. All my plots are off. So I'm going to type in my function, x to the fourth minus 4x cubed plus 2x squared plus 4x minus 3. And I'm going to try looking at this on just a standard window. So I'm going to go zoom and then number 6, standard. There we go. I might zoom in a little bit. So I don't know if you guys know how to do zoom box. I'll show you it. It's really reflecty. Maybe I can do that. That's a bit better. So to do zoom box, you click zoom and then number 1 is box. You see I get this little cross, the little plus looking thing. What you're going to do is drag it to like the top left corner that you want your new window to be and hit enter. And then you start to open that box and you just open it until you're enclosing everything you want to be shown in your window. And then you hit enter again. And it automatically adjusts that window to show you what you asked for the graph. Okay, perfect. So then I'm just going to sketch that on my paper. Kind of looks like a curvy W. I'm sure your sketches will look better than mine, but you're going to get the picture. Okay. And then I need to be able to locate those special points because I can see that my function is increasing and decreasing and then has some of those local maxes and mins. So my function, if I get on the roller coaster coming in from the left, it is decreasing until right here. There I have a turnaround. So we go decreasing from negative infinity to wherever this point is. And then we are increasing up to here. So we increase till we get to this point. And then we're decreasing again. Decrease until we get here, whatever that x value is. And then we're increasing again out to positive infinity. So we need to know what those x values are where we have local maxes and local mins. So here is a local min. There's another local min. And then here we have a local max. So we're going to need to figure out how to get those ordered pairs from our graphing calculators. So we will write those directions down. To find a maximum or minimum on the graphing calculator. This is a great way to check your work if you're asked to find them by hand, but also sometimes you're asked to just find them on the calculator. So once we have it graphed in the calculator, you're going to push the button second and then trace. So those are the buttons we're pushing. So second, and then the button we push is trace, but what we're actually wanting is a calculate menu. And then we're going to choose either maximum or minimum. So we push button 3 for a minimum. And you can read it on your screen. The main thing is knowing how to get to that screen and then what to do once you're at it. So let's do a minimum first. So I'm going to push 3. And then it's always going to ask me 3 questions. It's going to ask me for a left bound, a right bound, and a guess. So if I have a minimum, then at some point it looks like that. I'm looking for this point here. So that's going to be my guess. And then my left bound, I want to be to the left of that guess. My right bound, I want to be to the right of that guess. So I'm going to move my little spider. That's where my guess is going to be, but it's asking me for a left bound. So I need to go over here to the left side of that and hit enter. And then it wants the right bound. So I go to the right side of that and enter. And now it wants my guess. So I go to the bottom-ish and enter again. And then it's going to give me an ordered pair. So that ordered pair is negative 0.414, negative 4. So that means this x value is negative 0.414. That's what I needed to know to get my decreasing interval between negative infinity and negative 0.414, and then my increasing interval between negative 0.414 and whatever this number right here is. So let's go ahead and find that maximum then. So we do again, second trace, and we're going to choose maximum. Now it's going to ask me those same questions as it did on the minimum. This time my spider on the left will be over on that side, on the right will be over on this side, and my guess will be near the top. You can't see that. There you go. So I'm working for a maximum, and it says maximum at the top. So just double check and make sure you're doing always the right thing. Left bound is to the left of the maximum. Right bound, I got to go to the right of the maximum, and then guess right on top of it. That ordered pair, it says 0.9999996. That's actually the ordered pair 1, 0. So this x value right here is 1. And then I have to find this minimum. So I'm going to have to do that again. So second calc, minimum. Now you can also type in numbers like I can see that 2 is to the left. So I could type in 2 and enter. And then I could type in 4 and enter. And then I could guess 3. And it's still going to find it. But you can also trace along like we did on the first minimum. So this min is 2.414, negative 4. So that x value would be 2.414. Then I'm just going to use this graph to list my increasing and decreasing intervals. So this graph is decreasing on the interval between negative infinity and negative 0.414. And then it's increasing for a while, and then it's decreasing again between 1 and 2.414. We're always using x values to describe those intervals for increasing, decreasing. Then it is increasing on the interval between negative 0.414 and 1. And then again from 2.414 to infinity. I left you a lot of space here. We're actually done on this page. Okay, average rate of change. Average rate of change is a fancy way to say the slope of a line between 2 points. And we're going to learn a fancy formula for it as well. So if I have 2 ordered pairs on my graph, let's say I go up here from A, and this is the function f of x. So this ordered pair here would be A, f of A. And then I have my second ordered pair here, which is at B. So then I have B, f of B, whatever that number B is. I would plug it into f of x to get the y coordinate. Now, if I connect those two ordered pairs rather, I'm going to get a line, straight line. Now, this line is called a secant line. It connects those two ordered pairs on the graph. And we're going to use it to find the slope or the average rate of change between these two ordered pairs. So remember, the slope is rise over run. So we subtract the y's over subtracting the x's. So for our average rate of change, which is going to be slope, that's what we're going to use for our formula. We're going to take the y's and subtract them in the numerator, the x's and subtract them in the denominator. So our y's are going to be the y coordinate here, f of b, minus the y coordinate here, f of a. Subtracting the x's, the x coordinates were b minus a. So it's just literally still finding slope. One of the hitches is that they're giving me a function and not just two ordered pairs. So we have to generate our own function. So they're asking me here to find the average rate of change. That means the slope. We're going to be doing f of b minus f of a divided by b minus a. So we need our two ordered pairs. Let's say this one is A and this one is B. So I need to find f of A, which would be f of negative 2. So here's my function. Remember that when you substitute in, you replace those x's with your number in parentheses, please. So we got negative 2 squared minus 5 times negative 2 plus 3. So that would be 4 plus 10 plus 3. So f of negative 2 is 17, which is a fancy way to say the ordered pair is negative 2, 17. Then we'll do the same thing for f of b. F of b is going to be f of 6, which means my input is 6. So I change that to 6 squared minus 5 times 6 plus 3. So 36 minus 30 plus 3, which is 9. So f of 6 is 9, which gives me the ordered pair 6, 9. Then remember to find the average rate of change, which means slope. We're going to take f of b minus f of a over b minus a. So f of b was 9, f of a was negative 2, over b, which was 6, minus a. Oh, that was 17, y'all. F of b was 17. B was negative 2. I hope you caught that before I did. So 9 minus 17, which would be negative 8, over 6 minus negative 2, which would be 8. So that gives me an average rate of change of negative 1. Now, if they ask me to find the equation for the secant line that contains those two ordered pairs that I just found. So now I know that this ordered pair was -2, 17, and 6, 9. The equation for that secant line, that's this line that I just drew, except for it's on this function, which is a parabola. So the equation for the secant line is the line that joins those 2 points. So we need to know the slope, which we just found. So the slope is -1. And then we can use point slope form. So point slope equation, remember, was y minus the y ordered pair equals the slope times x minus the x coordinate. And we just choose either one of those points. It doesn't matter which one we pick. So if I do y minus 17 equals the slope, which was -1, times x minus the x coordinate. You could have also used the ordered pair 6, 9. It does not matter which one you use. So that's y minus 17 equals -x. This would make x plus 2 in here. So when I distribute that -1, it would be -x minus 2. And then add that 17 over. So y equals -x plus 15. And that would be the secant line.